Good morning, everyone, and welcome to today's webinar, What's New in Creo 9, Deep Dive Part 2, Simulation and Analysis. My name is Carolina Haig, and I will be your host for today's event, and presenting today will be Mikko Hinkanen.
For the webinar on my behalf as well. Today I try to run through the what's new in Creo 9 in the simulation and analysis side of it, and show a few demonstrations on the live software as well. So today's subjects are kind of a general introduction to Creo simulation environment, and then we go through the, let's say, 4 different applications, some side notes about what's possible today on the welding side. So if we think about what kind of a simulation applications we do have at the Creo Parametric environment, or kind of a couple to that one, we have classically Creo Simulate and Creo Simulate Advanced license in there. But then on the other hand, we do have a Creo Simulation Live application, which comes with the 2 different kind of a licensing level. Then we have a Creo Ansys simulation, which has at the moment just 1 license level, but there will be some more with the Creo 10, they've been told to us. Then on the other hand, we have a Creo Flow Analysis for the CFD applications, and that comes with 3 different application licensing levels. And then we have a Generative Solutions, which comes with the 2 different licensing level at the moment. So we have kind of a, let's say, a plenty of what to choose from, and it can be from time to time a bit difficult to reckon that what do you actually need, and we try our best at this webinar to make it visible that what's what and how do they differ and what might you need. So let's go for the Creo Ansys simulation then. What's new in there? So previously that came out with a few versions ago, and what's been happening here is that usability enhancements out there. So capabilities of copying and pasting simulation objects from the model tree, and from the study to another study, so you can have multiple of them in the one kind of model. And then second thing is the number of the CPU cores can be adjusted during the run. And then let's say everything is a bit more easier to handle. And then we have a bit more warning style labels here to highlight that something is not up to date or not really, going as expected. Then one kind of a new thing is the bearing load. What does it mean? That you can basically have a non-constant load height for your, let's say, circular geometry like a holes or pin, let's say, shafts, which then enables you to have a bit better kind of a representation of the kind of a bearing or similar event. And some limitations, of course, exist, like axial loads are not there, and basically this is applied only to solids at the moment. Then when it comes to result handling, we have now capabilities showing the deformed shape and undeformed shape, and basically scale this, the amount of the deformation if you want to do that. Then there's also a possibility to do a simulation query live on the window to ask points, click some points and ask what's the value in there. So basically the result manipulation visualization is getting a bit easier at the moment. Further on, if you happen to put those simulation probes in there, which what I mean with that is those kind of annotations which indicates a local value. Like in here, it's a kind of deformation, or in here, it's a stress. You might see this flag in here. And previously, it was a bit hard to tell that, if you make multiple simulation runs, that if some of those basically were outdated, so basically showing a wrong value. So nowadays, we have a flagged out everything that you have to rerun it in order to make the results to be on time. So hopefully that gives you a better kind of fun control of your results, and helps guarantee that nobody is kind of looking for old results when you should basically rerun everything. Then we have something which is called inertial relief. It simply means that if you are having this kind of fun, let's say, a link, basically, you have a kind of a mechanism attached to from the 3 sides, maybe some dampers, maybe some cylinders, and it moves into space. it is sometimes quite hard to constrain that. But on the other hand, what you can do always is that just calculate the forces affecting to this one, and then you are kind of having a force balance on it, and then we just have to limit somehow the residual forces off and residual moments off. So what you can do today is to put that inertial relief on, and system will automatically generate the acceleration field so that the sum of the forces are 0, and therefore we can calculate this without any kind of a constraints. And that has been also available, let's say, in Creo Simulate and other products for ages, but now it's also available in the Creo Ansys simulation. And then, as I kind of earlier kind of stated, that shells are now there. What we have there is automatic shell pair detection, which means that if you just have geometry like this in the solid, you can say that, let's say, search everything that is maximum of 10 millimeters thick, and then system will automatically find the pairs that are matching, and we're having a kind of a mid-surface compression to create shells. And then you can run the models in the shells rather than solids, which of course makes it much faster, but then on the other hand, you lose some details, but usually this is sufficient enough to make the shell model. Also, what we can do is do a mixed model, which means that we can mix up shells, beams, and solid elements together, and make the model kind of reflect the, how do we say, required kind of a solution accuracy in the way that we want. So that is what I'm about to show you next with the live software. Okay, I don't want to restart anything now. Let's go for 2 hours, remind me later. So in here we have pretty simple kind of a model. We have a one end plate. First we gather ourselves a bit of licensing here. So let's go now. We have a plate, well, it's a beam basically. Then we have an end plate, and then we have yet another end plate in here. And my plan is what to do is to have this model in here as a solid and the rest of the stuff as a shell. So if you go for applications, Creo Ansys simulation, what will happen is that you land in here, this kind of environment, which looks kind of pretty similar what you have had, for example, in Creo Simulate earlier on. You have your kind of constraints, you have your new bearing load in here. And now what's new in here is that today we have, for example, review geometry. If you click that, you can see that, okay, some of things are solids. If you click apply, these are solids. And when it comes to shells, these are shells. Should you have a weld surfaces, they would have this color. Then on the other hand, how do we connect these things together? As you can see, we have a bonded surfaces and bonded edges highlighted in a bit kind of a cyano-magnetic color in here, also in here. So basically what you can do is bond these elements together. Then, should you mesh this thing, you end up in the shell mesh. As you can see, there's no thickness in here, even though original geometry had it. Since because thickness is kind of a numeral in this one, but on the other hand, in here we do have a volumetric thickness since this is solid elements. And when you go for results, let's go for displacement, just activate it. This is already pre-run kind of a thing, and you will see that, okay, we have our deformations. If you want to scale your deformation, let's say 5 times, you really get deformed structure in here. I don't want to have the auto scale door in here, or just want to play it back and forth. Let's put something like 2 times and try to play it. You will see that it gradually goes down, and yes, we can also adjust the speed of it with this one. So there's some new tools for you to play around. Was there anything else? Shell creation itself. Well, if you want to do shells, you can do them from the surfaces. You know, just click the surface, what you do with the surface modeling, and define that what is the material property and what is the thickness of the shell. On the other hand, shell pair, you are manually pointing out these are matching the pair, which is then compressed to mid surface. On the other hand, you can give out the number, and then system will automatically find all the matching geometry that might be. Then what else there might be? Well, from this point, I would say not much from it comes to Creo Ansys simulation. These are pretty much all the new stuff. Then we jump back for presentation. And go for a new application called Creo Simulation Live. So what's the difference between these two is that Creo Ansys simulation, you really compute with your CPU, but with the Creo Simulation Live, you run the computation at your display graphics card. And so they are a bit faster. And in general, what we have here is temperature, capabilities. You can today assign temperatures and all that. And basically, the physical phenomenon what we try to simulate here is temperature expansion, and you can do that in real time with structural loading. So both of them at the same time. And you need a Creo Simulation Live Plus license to make this thing happen. And only available as a steady state thermal, which means that you cannot basically vary the thermal things over time. Then the second thing we have in here is the lattice geometry. So in the 3D printing, it's typical to have some kind of a lattice in the system, either kind of a beam-like or kind of a gyroid shape or something like that. And now what we do here is just define that, okay, remove internal geometry from here. And if this happens to have that kind of lattice in there, then it's possible to remove that from the computation domain, which means that then the flow has to go on this kind of a curvy path from one end to another. And you can simulate then the results of, as you can see on the lower right corner. Further with Creo Simulation Live, what we can do today, as we can do in the basic Creo application, is split the surfaces so that in here, for example, we don't have to make a constraint to the whole surface. We can just use a part of the surface for the constraint, which then leads a bit better representation of the surroundings and therefore a bit better stress kind of related results. On the other hand, what is still kind of a futureware or promiseware is that at the Creo 9.0.10.0, there will be contacts, which then, of course, will help us to kind of describe the surroundings even better, to have multiple pieces which kind of contact and are able to separate as well, should that be possible when it comes to force balance. So that gives you another edge to when it comes to using this Creo Simulation Live to make it even more realistic. And then basically as a final note for the Creo Simulation Live, I will show a short demonstration about this fluid floating. We have this kind of a heat exchanger where the flow is coming in from the one end and leaving from the other. And then on the other hand, if you take a look at, there is some kind of fun lattice in here, which then makes the flow go here and there to thus make it kind of efficiently kind of fun distribute the heat to these ribs. And this heat exchanger is getting up. That's how it works. So let's now show that. Where's my, that might be the one. And then we open our model. And as it has some lattice geometry, it will take a few seconds to open up. Now we got the model. So nothing specific in here, but then when you jump into Creo Simulation Live environment, just click Live Simulation. You will see that there's a one structural analysis, but there's a one fluid analysis made in here. In here, you could have this remove internal geometry button, which simply means that, okay, now we are taking care of all considering that lattice geometry in there. Then we have a boundary condition, which says outlet pressure is 0 bar resisting, and then you put 1 kilogram per second in, and then you have a general initial temperature in here. And basically everything is prepared for us to make it run. So we just click, simulate. And if you consider how fast this is to the traditional CFD, well, let's think about first of all the meshing. It would take some time to mesh this thing. and do everything. But in here, we just wait for, let's say, a minute or something, and we are about to have initial results already. As you can see, the initial results are now developing. The system is trying to find the stable kind of stationary velocity distribution in here. And we are about to have our results in here. Should you want to look at what's happening inside, you can click cut plane, and the trick of the trade in here is to just go for fluid objects from the smart filter and click the plane. Then you can get this arrow and drag it so that it is actually in the middle of things. So what we can do is see what is happening inside here. As you can see, the fluid pattern here is getting quite complex. And then on the other hand, if you want to have a direction field, the same thing applies. If you just click it and then just drag it, you can see kind of the swirls that where are we going, what is the direction of the fluid in here. And the swirls are shown quite nicely here as well. So basically enabling you to go through the structure. Let's close that one and go back for our PowerPoint presentation. Ooh, I swap again. So a few words about Creo Welding. So on the previous kind of presentation, I showed you the same kind of slides, but repetition is sometimes good. What can be done today with the welding is that we do support kind of the trajectory paths export to the XML format, so that this can be used from the offline programming of the welding robots, so to speak. At the moment with the Creo 9, we support only the fillet welds, but basically all the types and kind of attributes of it. But on the other hand, later on there will be some other welding types supported as well. Then on the other hand, support of the exporting the mass properties out for some other use, for simulation use or something like that is possible today with Creo. You can export everything out by the CSV or common separated values or the XML format. And then back to simulation topic a bit more. What we have is Creo flow analysis next. Well, and that is basically a typically CPU-based application. We do have 3 different license level here. And if you think about flow analysis basic, we have everything what, let's say, basic engineer needs. We have a heat transfer in here. We have a turbulence models in here. Should you want to find out what are the particles lands, if you have a radiation, thermal radiation at your model, if you have a multiple, let's say, gases like carbon dioxide and air and such, if you want to see how are those fractions distributed over the fluid domain, that's also possible with plus license. And also if you have some moving sliding meshing, which means that you want to simulate some kind of an impeller or fan or maybe some piston, that's possible with Creo analysis, flow analysis plus. And then if you go a bit more advanced kind of topics like cavitations, you might have a multi-phases in there. You might have a multi-components and dynamics. Those are possible with premium license level. So it is not a single kind of a product at that, so you always have to kind of take care of, take a look at the level of licensing, what is required for the job, so to speak. But nevertheless, let's look at the enhancements what we have in here. So with the Creo 8 and earlier versions, what you had to do is to just have a single project per assembly file, and that is a bit limiting factor. So with the Creo 9, you have a capability to have a multiple project per assembly file, which of course, and it gives you some flexibility to have a multiple, let's say, scenarios in the just one file. And yes, of course, you can activate the one and what you want to have. So you have, let's say in here, initial project, then you have test 1, test 2, test 3. Of course, only one can be active, and let's have a simulation. And should you just want to vary the project a bit, you can of course copy and paste or duplicate the existing projects as well. So it gives you a bit more leverage on that. Then the view panel. It would help you to kind of control what do you see, what kind of results do you want to see, the grid lines from the mesh, do you want to see some, transparent geometry, which side of the surface or cutting plane you want to see. So kind of a general post-processing is now basically well written. So there's a new set of tools for everyone in there to make the result handling a bit easier. Then what else? The units, previously the units were a bit, let's say interesting, since we didn't really see any units anywhere. So we just had to know that since you have millimeters and kilograms, then therefore the derived units are such. Or then you might also, let's say in meshing, you might have to give out measurements in meters, which then requires that you have the multiple leading zeros in there. But today we can, we support the units, which makes it much easier for the people to put in the proper numbers and get in the correct results as well. Then on the other hand, if you look at, in this case, the fluid domain, and so basically this is external flow, velocity comes in here with certain temperature, and then we have resisting, pressure in here. You can actually see these things on your screen all the time while defining a simulation with the proper units as well. So it's easier to put the model or set up the model properly so that it actually simulates what you want and you are not making mistakes with units. Then post-processing, as I tried to tell you earlier, basically post-processing is rewritten, all kinds of dialogues and the controls handling the results are now changed to make it easier to understand it, or make it easier to manipulate the results and create different kind of a result as well. So in here you can maybe see the pressure distribution and here the velocity distribution for your design. What else do we have? Legend levels can be controlled as well if you want to, limit the maximum value, minimum value, so that the color gradients are, let's say, a bit sharper on the area that you want. You can limit them. And on the other hand, the units of them as well. And there are a lot of kind of fun, let's say, easier approachable controls than previously was. So post-processing is basically rewritten for the Creo 9. And then in here as well, the lattice geometry is supported. They are shown here as a hybrid bodies. So if you go in there and look at the geometry and you want to include that, let's say, a lattice in here as we have, then you just have to have a hybrid bodies as a yes, and then fluid volume will be automatically generated to take that account. Otherwise, you don't get anything in here, which is not really the kind of a simulation you want to have. What else do we have? Oh, a kind of a cross use of existing Creo parametric capabilities and the Creo flow analysis is that if you happen to have a behavioral modeling extension, which basically is a geometry optimization extension for the Creo Parametric, where you can, let's say, study that if I change these dimensions or these parameters, what will happen to outcome parameters, and then you can basically minimize the mass or minimize some other function or maximize some other function. So just try to find out if something is feasible, or can you do, or let's say, change these dimensions and get that one result, let's say. But today, what's been happening is that with the Creo flow analysis, we are now able to create parameters from the geometry, but on the other hand, we are able to generate some output parameters like, let's say, a pressure or something like that, or velocity or mass flow from that analysis, and use them in the behavioral modeling. And as a simple kind of example here is that if you have this simple ball valve, if you have it, let's say, partly open, if you just want to run the pressure of the inlet from the 1 bar to 6 bar, and then you just want to know that what is volumetric flow over it, you can create an analysis using the Creo flow analysis functionality, but also using the behavioral modeling extension. And then the behavioral modeling extension is capable of plotting out the sensitivity plot of what is the outcoming flow cubic meters per second when the input pressure varies over the from the 1 bar to 6 bar. So it's a kind of a, let's say, handy tool to find out what is the optimal spot, or if something exists on particular kind of capabilities, or how much should I basically change something. So if I want to, let's say, have exactly 4.5 bars, let's see what is the flux in there, or other way around. If you want to have, let's say, 770 is the liters per second in here, or 7 liters per second, then you have to have 2 bars in there, basically the pressure difference over the bar. And then the last one I want to speak about is generative topology optimization. This is a new module from the few versions ago. New things what we have here is the previously what we did was basically look at the strain energy and optimize the things with that. But the problem was that stresses could go way above the yield point, and let's say the design propositions that what system gave to you were kind of nice, but on the other hand, they were exceeding the allowable stresses. So today, what we have is basically minimize the mass with the safety factor, and this is safety factor against the yielding. So it simply means that, let's say the stress is in here, as you can see, around 300 megapascals. If you say a factor of 2, so we have assumption this could maybe hold at 600 megapascals without breaking. So minimize the mass by doing that. So try to make it as smooth geometry as possible, but keep the safety factor against the yielding for the 2, and make it as light as possible. And then the system is basically finding out the solutions within this solution envelope, so that these areas are kept, and please reduce everything to minimum. What else there is? Previously we had a structural analysis only. Now there's a model as well. So for some applications, vibration is important, so that if even though you would have a nice let's say geometry which will hold the loads, but if it starts to vibrate, it's basically useless. So we can also today make a first or second, let's say, model frequency or model shape, so that you have limitations in there, so that the vibration studies are also kind of concerned while designing these geometries. What else there is? Then as a ease of use functionality, or basically let's not waste the computational effort, is that we can run the initial simulation, which simply means that, okay, system will just run it basically once and just post you the results, so that you can see that, okay, I have put my, let's say, stresses correctly or forces correctly, I have my boundary conditions correctly, so the model is behaving according to expectations, before you say to system, okay, let's start to optimize, because sometimes optimizations can be taking an hour or more, so it would be a bit kind of fun, let's say, useless to make the computer run for the simulation that is not really the one that you made due to some mistake of the inputting the parameters or inputting the constraints or forces. Then as a new kind of less functionality in the presentation is that we have a ball constraints also available for the spherical surfaces, so that the translation is fixed, but rotations are free, and this of course enables us to kind of describe some of the movements a bit better, and thus getting a kind of a proper description of what's happening in the model and for the optimization as well. And then let's try to show you some of that as well, if I still remember what I have to show. Not the file open as a working directory. I think it's just this one. Then we go for, I have one funny number series here somewhere. I have a few models in here. Let's say what we can do in here. So if you look at the model in here, it's pretty much just the design envelope. If we go for this design items, you will see that there's a multiple bodies, there's one imported, there's something preserved, which means that these areas you must basically keep. So looking like that. And then they have made a basically a starting geometry. So this is the volume you have to keep yourself in, and then at the end of the day we have exclude body in here, which means that you cannot go on this area. So basically it's a cut against that one, but let's hide that as well. So if you go for application and you go for generative design, you will see that somebody has been doing some work here already. You have classified the geometry for starting body, or basically the volume to search for. Then on the other hand, preserved are those blue areas. And then we have exclude one in here, which is not even shown. Let's show it for the few seconds. You cannot go on this area at all. It's just hidden for the simplicity. And then what we have here is a few cylindrical kind of a coordinate system, few planar, so to keep it in, basically bolt it in. And then what you have here is forces, just one force on that pin. And let's go for design criteria in here. Actually clicking from here. And as you can see, default is maximize the stiffness, but this doesn't take care of the stresses. But if you want to say maximize the mass, you have a safety factor on the plane based on the material data. Should you want to have some additional constraints like a building direction for the 3D printing, maybe parting line, maybe something that can be machined from the one side, or if you want to have a symmetry, or maybe the radius in here for the kind of geometry that comes, you can have all of these or just one of these as additional kind of limitations. More you add of these, of course, computation times gets longer and longer. Then the materials, you can have, simulations just one material by the time. But if you go for these cloud-based applications, then you can have basically multiple materials here listed. But at the moment, I'm just doing to minimize the mass with safety factor of 2. And now basically everything is defined. And then if you say study settings, of course, how kind of small details you want to see, it depends on the mesh size. And due to time factor limitations we have for today's presentation, let's go with the easy one. So, and now I say just to optimize and try to calculate it while we look for that if we have any questions at the moment. Do we have, Caroline, any questions at the moment while the computer is running?
No, we don't have any questions at the moment.
Nevertheless, thank you for that. So as you can see, the geometry is gradually forming. You still have some funny things in here, but optimization is just 1% gone. And system tries to cut down the volume as much as possible while keeping the safety factor at the level of 2. And this will take, let's say, a minute or two to run through. But the idea with the generative topology optimization is that you can have multiple load cases and you can optimize your design against something, and then you get a fully kind of fun functional 3D model, which you can use as is, or basically use as a base for your design for the exact component that you might want to have. But it kind of does the job autonomously. You don't really have to care about anything at the moment. Just tell that what there are the limitations, and then computer will take care of the computing and finding out the optimal shape for you. And sometimes the results can be quite surprising that, oh, you can do it like that as well. But enough limitations, you can basically do the things with the, let's say, like a sheet metal things or something like that. And sometimes it's good to understand that this is not necessarily manufacturable geometry as is, but you still can use this as a base of kind of fun designing your own component and consider the manufacturing limitations and all that while you design. You just get the overall shape with this generative topology optimization. Do we have any other questions? Not yet, anything?
No, not yet. We're waiting here in suspense for you.
Well, since I run out of my slide deck, so we can of course take a look until the end at how this does go forming. As you can see, these both kind of surroundings are getting kind of nice colors around them. Colors, let's say like that, not colors, colors. And the geometry is gradually shaping up. You still have some funny lumps in here, but nevertheless, it's getting smoother and smoother. And here's happening something funny. There's a hole. Let's see what will happen on that one. And now we have a second hole. So this starts to look a bit like a, let's say, organic, like a bone or something like that. But my first guess is that the non-regular, let's say, regular mechanical engineer wouldn't at the first go land on the structure like this. So it gives you kind of a hint about that. So we got microfluids when it comes to question in here. I would say no, but it depends now on your scale of what do you mean exactly. So I got the question from if the microfluids are supported in CFD that is creeping, you know, around very small structures, and I would say no. I will try to gather some info about that requirement and get back to you, Patrick, about this. And I have done something like 70% of the simulation. And as you can see, the geometry is gradually forming. Now we have a large void or opening in here, but also in here. Now its second opening is coming up. So we're gradually limiting the mass. We started around 1 kilo and now we are around 400 grams. But maybe as you can see, this will take something like maybe 5 minutes to compute. If you have a multiple variables and all that, then there's a possibility to send to cloud with the license extension and make the cloud do the computing. If you have a multiple kind of a design, like a materials, multiple load cases, multiple kind of criteria you might want to have, then the cloud platform solution also exists. So you don't have to basically overload your local laptop. And in here, if you look at the very close look, you will see that there's a 2.009, the safety factor at the moment. Computation has been running for 6 minutes. And this is the alloy we're using, and the icing criteria are as such defined. And you might see a small gradual changes when the system is optimizing everything in here. Any other questions from the audience while we watch this movie?
No other questions at the moment, but feel free to ask any questions. Now is the time to really interrogate Mikko here and put him on the spot. So if you have any questions, put them forward.
Yeah. Well, now I got it luckily finished, so I don't have to just sit and wait. So thank you, Carolina, for that encouragement. As you can see, this geometry is kind of organic looking, suitable, you know, especially for the 3D printing and or maybe the investment casting or something like that. But then this is just the finished thing. Then on the other hand, if you want to see the simulation results about, okay, what is my stress level? Let's go for megapascal, so it's understandable. So there is something like if you click that one, there's around here at the one kind of very close to constraint, you have 120 megapascals, which is then guaranteeing as a safety factor of the tool for you. And here you have a bit less than around 100 megapascal stress level in here. Also same thing in here. But other than that, we are something like on the 60 megapascal level, which is quite okay for the design like this. And then if you want to, you can just click generate the design, and let's hope that we can make this thing run. So current part, let's go for these kind of things. So in the system, this is really at the moment a tessellated geometry, looking like a STL model, even though it's visualized very nicely for you. Then what we do is just say to generate the design, And what system will do is push it out as a, let's say, a kind of a STL looking like, also including the bodies that you might need, and then tries to make a kind of a mapping using that. What was the feature called? Freestyle maybe. Use a freestyle feature to map on top of it in order to create a C2 continuous surface set for you, which then basically gives you a total 3D body as a solid geometry. And now again, it's time to interrogate Mikko if you want to push some questions at the chat.
Go ahead. He's not that harmful.
So again, as you can see now, what we have here already, the results, we have the solid part for this particular problem. And of course, the question is, okay, how do I manufacture this? Well, 3D printing maybe. If you have, let's say, more, let's say, limiting manufacturing methods like a sheet metal or something like that, then you could also consider that, okay, if I weld something like this kind of a piece in here, then I may just have to use a kind of arc-shaped piece of sheet metal, which has a constant thickness, of course. Or if you want to mill it from above, then you just basically neglect all the voids in here. So it's kind of a starting point for your geometry optimization. Then at some point, hopefully we get a bit more manufacturing constraints here that are giving us even kind of a better solution for this. But in order to find out most efficient shapes for some, mechanical load cases or vibration load cases, this generative topology optimization is pretty nice tool for that. Should you not want to ask any more questions, then I say I'm done.
Fantastic. There are no more questions. So thank you so much for today's webinar, Mikko.
Thank you everyone for participating in this one.
Yes, and in case you missed any of our previous webinars, they are available on PTS Vision's on-demand webinars. So thank you very much for everybody for participating. Bye.
Bye.